Our final lesson in Chapter 5A is 5.5, Apply the Remainder and Factor Theorems. In this lesson, instead of factoring just completely from start to finish, you'll be given a factor, verify it, and then use what's left over to find the rest of the factors and even zeros of a polynomial. The process that we'll apply is long division, and then we'll apply synthetic division. Now, synthetic maybe sounds familiar because we did that with synthetic substitution. The process is very similar. But we start off with long division, and it's not just a catchy name. This is a long process. It says for division, all terms need to be present. Divide f of x equals x cubed plus 5x squared minus 7x plus 2 by x minus 2. So what we're dividing by is called the divisor, and that goes on the outside of the dividing bar. We put x minus 2. We draw a really big dividing bar. Notice I've left some space up above. We're going to put some work there. And I'll put the original polynomial on the inside. X cubed plus 5x squared minus 7x plus 2. Notice all terms are represented from the degree of 3 down to the constant. To apply the idea of long division, we want parts on the outside to equal and cancel out with parts on the inside. So here's the process. Underline that first term in the divisor, plain x, and then underline the first term in the polynomial, x cubed. What could we multiply x by to equal x cubed? We could multiply it by x squared. What I'm going to do then is put that value up in the column where the x squared term is in the polynomial. So just kind of in that spot right there. Then we're going to distribute it to both parts in the divisor. X squared times x would become x cubed. Match it up with your column. X squared times negative 2 would be negative 2x squared. That matches up in the second column. What we're going to do here is figure out the difference, or what's left over. To do that, we have to subtract both of the terms, which means I'm going to make x cubed negative, and then that ultimately changes the negative 2x squared to positive. We have to change both signs. When we do that, the x cubed cancels out. And what's left over in the next column, 5x squared plus 2x squared would be 7x squared. And then we drop down the next term, minus 7x. We complete this process until all the terms have been kind of represented or accounted for. Again, have your first term on the outside underlined, and now let's underline the first term on the inside. What could we multiply x on the outside by to equal 7x squared on the inside? Well, we'd have to multiply by a 7 and an x. I'll take both of those parts in that term and distribute it to both parts in the polynomial. 7x times plain x is 7x squared again. You always want that first term to be an exact match. 7x times negative 2 becomes minus 14x, and draw your line. Then remember what we do? We subtract this row to find the difference. So that means I make that first term negative, and that second term will actually become positive again. And the first column always should cancel out. Let's see what's left over. Negative 7x plus 14x would give us positive 7x. Drop down the constant. So once you drop down that last term, this will be our last process for the division. One last round, we have x on the outside, 7x on the inside. What would we multiply plain x by to get 7x? We'll multiply by 7. And now just one more round. You really don't have to do these arrows. It gets kind of tedious, but at least you know exactly what you're going to multiply by. 7 times x, we get that perfect match. And then 7 times negative 2 becomes negative 14. Draw your line. One last round of subtraction to see what's left over. If we change the 7 to negative and then that 14 becomes positive, we have a constant of 16 left over. And 16 is known as the remainder. Now the answer when you divide is called a quotient. So our quotient for this division problem is the number, or is the polynomial that's on the top of the division bar. So our quotient is x squared plus 7x plus 7 with a remainder of 16. See, I told you, that's long division. Naturally, it makes sense that we should try one more. Divide p of x equals x cubed minus 1 by x minus 1. So remember, whatever we're dividing by is the divisor, and that goes on the outside. If we put x minus 1 on the outside, and then put the dividing bar, all terms need to be present on the inside. If we write out the x to the third, notice we're missing both x squared and plain x before we get that constant of minus 1. That means we have to include those placeholders like we did before in synthetic substitution. So division is like synthetic substitution. All terms must be present. And now that we know that process, let's go ahead and start the division. Take the term on the outside, x, and then the first term on the inside, x cubed. Kind of like before, we'll multiply that by x squared and distribute it to both terms. X squared times x becomes x cubed, and x squared times, oops, I already did that arrow, negative 1 would be negative x squared. When we draw our line and change the operation for subtraction, and then this one becomes plus, our first term cancels. Now our second term, we have 0x squared plus x squared. So 0 plus 1 technically would just keep that as 1x squared. So think about that plain x squared like a 1x squared. And then drop down that next 0x placeholder term. And let's keep going. We have x on the outside and just 1x squared on the inside. What can we multiply plain x by to become x squared? We could multiply by an x and distribute it in. So it's a very consistent process. It's just a little tricky and takes some time. X times x becomes that x squared, and x times negative 1 becomes negative 1x. Draw your line, subtract them to cancel out that first term. The second term actually becomes positive. Cancel out that row. 0x plus 1x is now 1x, and then we drop down that constant, arrow, minus 1. Whew, one last time. All right, so notice x minus 1's on the outside, and we want to match it with x minus 1 in the bottom row. So x to get x, if we multiply everything just by 1, distribute it to both parts, we get x minus 1. And when we subtract, watch what happens. We change the first sign and the second sign, and not only do the x's cancel out this time, but so does the constant, and we have 0 left over. What that tells us is there's no remainder. That also tells us that x minus 1 goes into x cubed minus 1 evenly, and that's going to mean something significant when we try to solve. Our quotient then is x squared plus x plus 1. And we'll utilize that quotient in the remainder and factor theorems. The remainder theorem states if a polynomial f of x is divided by x minus k, this is our divisor, then the remainder is going to be whatever you'd get if you plugged in k into the polynomial. What that means is we can utilize a synthetic division option instead of a long division option, and that would help us determine our quotient a lot faster. Remember, with synthetic substitution, we just use the coefficients and then we go kind of up and over with the row with the multiplying and adding. Those numbers at the bottom are actually a significant part of our solution. Let's see how it works. Divide f of x equals x cubed minus 5x squared minus 2 by x minus 4. But instead of long division, we're going to try synthetic division. And then we're asked to state the quotient and remainder. Now it says since x minus 4 is the divisor, we're going to figure out what value of x to plug in to synthetic division. If we set x minus 4 equal to 0, we would actually plug in positive 4. So when we think about that number that goes in the corner, we're going to plug in whatever the x-intercept or solution to the divisor would be. I'll put 4 over here on that left-hand side, and then I'm going to put that little kind of divider symbol over here around it. Just like long division, we need to make sure all of our terms are represented. We have an x cubed, we have an x squared, but we're missing the x term. So we have to be mindful of that as we set up our synthetic division. Now the coefficient in front of x cubed is 1, so I'm going to start with 1. Then I've got negative 5x squared, so negative 5 is going to go next. Our x term was missing, so we need a 0 placeholder, and our constant is negative 2. This is the exact same process that we did with synthetic substitution. Draw your line down below with some room for work in between. Remember, the process for synthetic division matches up with synthetic substitution. Take that first coefficient and drop it below the line. Multiply that line with the number in the corner, 1 times 4, and that's just plain 4. That goes in the next column. Negative 5 plus 4, we add them together. You get negative 1, drops below. Negative 1 on the bottom times 4 in the corner becomes negative 4. Now 0 plus negative 4 would be negative 4 below the line. Last but not least, negative 4 times 4 in the corner would be negative 16. Negative 2 plus negative 16 is negative 18. Remember, in synthetic substitution, negative 18 was our output. Now, negative 18 is going to be the, you guessed it, remainder. And the numbers in front of the negative 18 represent the numbers for the quotient coefficients. Here's how it works. Whatever your lead term exponent is, or the degree of the polynomial, the quotient is going to be 1 less degree. This first number is going to be the first number for the quotient terms. 1 times x squared. Then it's minus 1. That means we're going to go 1 less x. And then negative 4 is the constant for the quotient. So that means x minus 4 goes into x cubed minus 5x squared minus 2. And we have a quotient of x squared minus x minus 4 with a remainder of negative 18. If you get a remainder, one thing to note, x minus 4 is not a factor. That means this graph actually doesn't cross the x-axis at 4. It won't cross because we have that remainder. The nice thing about synthetic division is that it allows you to not have to do long division, essentially. But if you have a remainder, it's really not helpful for you to solve the entire polynomial. The factor theorem is where synthetic is more useful. It says a polynomial has a factor x minus p if and only if f of p equals 0. So what makes this one unique is that you're not going to have a remainder. That means you can take the quotient and try to factor further. All right, so here's how we're going to apply this idea. Given the polynomial f of x and a factor of x, factor completely. So that means we should get a remainder of 0 this time. If x plus 10 is our divisor, we're going to plug in whatever the x-intercept should be. Oops, I'm saying too many words. So we're going to plug in x equals negative 10. If we set x plus 10 equal to 0, it would cross at negative 10. All right, let's put that to the test. Negative 10 is going to go in the corner. Put our little dividing bar, like so. Now let's take a look at our coefficients. Do we have all of our terms present? X cubed, 18x squared, 95x, and 150. Ooh, those are big terms. Can you imagine graphing this? This crosses the y-axis at 150. That's aggressive. All right. It looks like all the terms are present. Remember, the number in front of that lead term is just 1 if it's not listed. And then we jump up all the way to 18, everybody. Wow. And then 95, and then a whopping 150. Our goal is to get 0 as a remainder, and that will verify that x plus 10 is a factor. Lots of terminology thrown out here. Drop that first number straight down, 1. Multiply to the corner, 1 times negative 10. That goes in the next row. 18 plus negative 10 would essentially be 18 minus 10, which is positive 8. If you multiply positive 8 by negative 10, we get negative 80. And that goes in the next column. 95 minus 80, or plus negative 80, however you want to state that, would be positive 15. 15 times negative 10, wow, look at this, everybody. Who'd have thought? We get negative 150. Positive 150 minus negative 150 is, in fact, 0. That verifies that the remainder is 0 and that x plus 10 is a factor. All right, so now to figure out our quotient, what's left over? Remember, the quotient is always going to be 1 less degree from the original polynomial. The first number in our bottom row is 1. That's going to be the coefficient in front of the x squared term, 1x squared. 8 is positive, so I'm going to put plus 8x. And then there's a plain plus or positive 15, so plus 15. And then there's no remainder. If that's the quotient and you're asked to factor completely, we have to factor the quotient. So we have x squared plus 8x plus 15. This is quadratic, and we have all terms in the quadratic, x squared, x, and the constant. That means we're going to take the constant value, 15, and split it up. What are numbers that go into 15? Well, we only have a couple of pairs of factors, 1 and 15, or 3 and 5. Do either of those pairs give us 8 in the middle? Hopefully you recognize 3 and 5 would do that. That means that x squared plus 8x plus 15 would split apart into x plus 3 and x plus 5. You could write them in any order. We were asked to factor completely in the directions. At the bottom it says write as a product of factors. So remember in 5.4 when we did our factoring by grouping, we did our common factors, we did our perfect cubes, we wrote our answer as a product. Now the original factor was given, so we'll start with x plus 10. The factors that we generated are x plus 3 and x plus 5. When asked to write as a product of factors, that's what you're looking for. And I think that's probably a good stopping point for us now. Let's let that sink in, and then we'll finish the lesson tomorrow.